Have you ever come across a number like the square root of 2 and thought, what exactly is that? It doesn't seem to be a whole number and it doesn't seem to be a fraction. And if you put it into a calculator, you get something like 1.414 blah blah 2, it keeps on going. So why don't we just call it 1.414? Well, that's where surds become interesting. Let's start with the most important question. What is a surd? Well, a surd is just an irrational number that contains a root which cannot be simplified into a rational number. For example, the square root of 2 is a surd. The square root of 3 is also a surd, and the square root of 5 is also another surd. But the question is, why? Let's look at the square root of 4. The square root of 4 is a 2, and that's a whole number. So it's not a surd. And the square root of 9 is a 3, and again, a whole number, not a surd. But the square root of 2, there's no whole number that we can multiply by itself to get exactly 2. And there's no fraction that gives us the exact value either. That's because the square root of 2 is an irrational number. It's a decimal expansion that continues forever without repeating. So why not just use its decimal value? Because decimal approximations aren't exact. Because the square root of 2 is not exactly 1.41, it's not exactly 1.414, and it's not even exactly 1.41421356. Those are only approximations. The square root of 2 is just exactly the square root of 2. And this is one of the biggest reasons surds are used. They allow us to keep exact values instead of replacing them with approximations. Imagine a right angle triangle with two sides of length 1. Using Pythagoras' theorem, the length of the hypotenuse is the square root of 2. If we write 1.414 as the answer, we've introduced a certain error. But if we leave the answer as the square root of 2, we have the exact length. So surds are not just strange looking numbers. They are a way of keeping mathematics exact. But here's another question. Can surds be simplified? Well, absolutely. Consider the square root of 8. At first, it might look like we just have to leave it alone. But 8 can be written as 4 multiplied by 2. And the 4 is a perfect square, right? So the square root of 8 can be separated into the square root of 2 multiplied by the square root of 4. But if we look at that correctly, the square root of 4 is a 2. So that's just 2 square root of 2. But why is that useful? Because simpler expressions are easier to work with. Let's try another one. Suppose we have the square root of 18. Can 18 be broken down into a perfect square multiplied by another number? Yes, of course it can. 18 can be written as 9 multiplied by 2. The square root of 9 is 3. So the square root of 18 can be 3 times the root of 2. Now, let's try something slightly more challenging. What about the square root of 72? We look for the largest perfect square that is a factor of 72. That perfect square is 36. So 36 can be multiplied as 36 multiplied by 2, and that would give us 72. Okay, let's say the square root of 66 is a 6, right? Therefore, the square root of 72 simplifies to 6 times the square root of 2. Notice the pattern. When simplifying a surd, we're basically looking for perfect square factors hiding inside that number. Now, here's where things get interesting. We can add surds together, yes, but only when they are like surds. For example, suppose we have 2 times the square root of 3 plus 5 times the square root of 3. Because both terms contain the same square root of 3, we can combine them. Just kind of the same way we use variables. 3x plus 2x is equal to 5x. So that's going to be 2 plus 5, which gives us a 7. So the answer is 7 times the square root of 3. It's very similar to collecting like terms in algebra. But what happens if we have the square root of 2 plus the square root of 3? Here we cannot combine them. They are different sides, just the same way we have unlike terms in algebra. So yeah, we cannot add them. Now, what about multiplication? That's a little easier. Suppose we multiply the square root of 2 by the square root of 8. We can combine the numbers inside the root. 2 multiplied by 8 gives 16. The square root of 16 is 4. So the answer is simply a 4. And this is a useful property of sets. When multiplying square roots, we can combine them into a single square root. But division can be a bit more interesting, to say the least. Suppose we have 1 divided by the square root of 2. Is that an acceptable answer? Mathematically, yes, but we often prefer not to leave a square root in the denominator. So we use a technique which is called rationalisation. So what does rationalisation mean? It means changing the expression so that the denominator becomes rational. In this case, we multiply the numerator and the denominator by the square root of 2. The numerator becomes the square root of 2 and the denominator becomes 2. So 1 divided by the square root of 2 becomes the square root of 2 divided by 2. We've removed the side from the denominator without changing the values of the expression. But why are we allowed to multiply by the square root of 2 on both top and bottom? Because we are effectively multiplying by 1. The square root of 2 divided by the square root of 2 is 1. Multiplying an expression by 1 doesn't change its value. Now, let's take things a step further. What happens when the denominator contains something like 3 plus the square root of 2? This is where things called conjugates become a bit helpful. So the conjugate of 3 plus the square root of 2 is 3 minus the square root of 2. You just change the sign in between. When we multiply an expression by its conjugate, something interesting happens. The middle terms cancel, and we're left with a rational number in the denominator. This technique is especially useful when solving more advanced SAT problems. Let's see how SATs can actually appear in a problem. Imagine you're given a right angle triangle. The two shorter sides have lengths of 3 units and 4 units, right? And then they ask you to say what is the length of the hypotenuse. Using Pythagoras' theorem, we square the two shorter sides. 3 squared gives 9, 4 squared gives 16, and then we add them together, we get 25. The square root of 25 is a 5, so the hypotenuse is exactly 5 units. No sides this time. But what if the two shorter sides were 3 units and 3 units? 3 squared is 9, and another 3 squared is 9. Add them together and we get 18. The square root of 18 is our answer. But we know how to simplify it. The square root of 18 becomes 3 times the square root of 2. So the exact length of the hypotenuse is 3 times the square root of 2. A calculator might give us approximately 4.24, but 3 times the square root of 2 is exact. And that distinction is extremely important in mathematics. Now, let's try a more algebraic problem. Suppose we have the square root of 50 plus the square root of 8. At first, these look like two completely different sides, but let's simplify them. 50 can be written as 25 multiplied by 2. So the square root of 50 becomes 5 times the square root of 2. 8 can be written as 4 multiplied by 2. So the square root of 8 becomes 2 times the square root of 2. Now we have 5 times the square root of 2 plus 2 times the square root of 2. These are like terms, or like sets. So they combine to give 7 times the square root of 2. And that's the key idea. Don't rush to calculate the decimal value. First, look for the structure. Look for the perfect square factors. Look for like sets. Look for opportunities to simplify. So why do sets even matter? Because mathematics isn't always about finding a decimal answer or a fraction. Sometimes the exact form is more useful. The square root of 2 tells us exactly what a number is. 1.414 only tells us approximately what it is. Sets appear naturally in geometry, trigonometry, algebra, coordinate geometry, and many other areas of mathematics. Whenever a calculation produces the square root of a number that isn't a perfect square, sets can give us a way to keep the answer exact. So the next time you see the square root of 2, don't think of it as an awkward number that your calculator needs to deal with. Think of it as an exact number with a structure that you can work out. Okay, now we've reached the end of our video. Don't forget to smash that like button, subscribe to the channel, and hit the notification bell so that you don't miss out on any other content. Till next time, success through synergy.